Hello and welcome to our example discussion on what we call topic 9, which is on ANOVA. Now, in this video, we are calling it B because part A was already introducing the concept, walking us through slides where things have already been calculated for us, and we're more focusing on the concept behind this analysis of variance method. In this video, we are going to slowly work through an example by hand to see each of the steps in the hypothesis testing procedure and the calculations involved. As usual, we are referring to the Statistics for Psychology book, great explanations, wonderful book regardless of your specific focus for learning statistics. We are going to page 368 and we're looking for number 17. Whoa, that was aggressive. Where is number 17? I lost it because my PDF viewer is being naughty. There we go, 17. Let's fit it nicely on the page here at the top and read it just first, get the idea, and then we will think about it more carefully. Do students at various universities differ in how sociable they are? 25 students were randomly selected from each of 3 universities in a region and were asked to report on the amount of time they spent socializing each day with other students. So this is what we're measuring the sociability measure, however that's measured, for different universities to see if they are different. The result for University X was a mean of 5 hours and an estimated population variance of 2. For University Y, we had mean and estimated variance, and for University Z, we had a mean estimated variance. What should we conclude? Well, our hypothesis testing procedure, which we will follow step by step, will get us to a reasonable conclusion. We want to use a 5% alpha level, significance level, and the rest here, effect size and those I'll leave to you, and our explanation will just be done verbally as we go through the question. All right, so let's just set this up here. Number 17. Just shift my seat a little bit. There we go. That feels better. So we have our 3 populations. Population 1 that we're comparing by way of these samples of each size 25. Population 1 will be students from University X, and it's important, especially in the beginning, to write out these populations, have a clear understanding of the groups you're comparing, the groups you're investigating, that you're trying to make a conclusion about. So I have these 3 universities. Now, previously, if we looked at the t-test, this would be independent means t-test, then we were sort of restricted to only 2 groups. ANOVA you can see as the next step up, where I have more than 2 groups to compare to see if there is a difference. So then our null hypothesis, our research hypothesis, our null hypothesis will be that there is no difference between the means of these populations. And our research hypothesis will be that there is a difference somewhere. Now, I don't know exactly where that's going to be. Could be between the first two, could be between all of them. So we just write this research hypothesis in words. Do not have it be too clumsy, by saying not all the population means are equal. We don't know if mu1 is not equal to mu2. Just there's some difference somewhere. We don't know where or how many of them are different. So that's the setup. We're trying to compare. We're trying to make a conclusion about these groups by taking samples from each one and then investigating those samples. And we do it by comparing, in our comparison distribution, not looking at the means, but rather looking at how the variance between these three groups, that's a big 2, that was just supposed to be a little squared, how that compares to the variance within the groups. And we're going to call that the F statistic. So if there is a difference between the groups, then the variance within these groups, which we assume is all equal, will be different from if I just compare the groups between themselves. There's going to be some extra variation between these groups if some of them are actually different from each other. Then if I somehow sort of merge these and just calculate sort of a template variance within the groups. So that is what ANOVA is going to use. Now for these, we need degrees of freedom. Well, we are looking between the groups. We're sort of going up a level and viewing each of these as a single value, single point, single data point, and then we have 3 of them. So the degrees of freedom, which we'll call here between to distinguish, will be 3 minus 1 on, of course, a 2. The degrees of freedom within is where I sort of merge all these together, similar to what we saw in the independent means t-test. We're just going to add the degrees of freedom for each of the samples, which will each be 25. They said that we take 25 students from each of the 3 universities. So our sample size conveniently is the same every time. We take a sample here that's called N1 of 25, N2 of 25, and our third sample is also the same. So the degrees of freedom for each one is 25 minus 1. So we get here 24, 24, 24 for a total of 72. So we need these guys when we look at our F statistic table. So keep that in mind, and might as well do that right at the beginning and get it out of the way. So now the issue becomes, how do we calculate the variance between the groups and separately the variance within? And then we can compare them by putting them into the fraction and then comparing that fraction essentially against 1. 1 would be perfect, that they're the same and there's actually absolutely no difference. But of course, we have a sample, so there will be natural variation. And that's why we have this statistic and its distribution, the F distribution. So I find it easier to do the variance estimate for within, because I don't really know. I just find it a little bit easier to start with. Start with the easy things and then you get into it, and by the time you get to the more difficult things, you're sort of warmed up and more ready for them, I guess. So when we do the within groups estimate, we are merging them all under the assumption, part of the ANOVA theory, is that all the variances within the groups are the same. Students don't really differ. It's among themselves. The question is, from university to university, is there a difference? So I just want to get the best and most accurate variance estimate from these samples that I can. And similar to what we've seen before, we're just going to merge them conveniently. They have the same sample size, so it's going to be as easy as just taking all the variances and averaging them out, essentially merging the variance information from all the samples. So if I refer you to our formula sheet, that's going to be here at the bottom. You're just adding up the variance from each, of course those are estimates, from each sample, divide by the number of samples, the number of groups, and that is your estimate for the variance within the groups by merging them all. All right. So that is fairly straightforward. I hope you agree. Let's just actually do it. So I'm going to try and squeeze it in here. Our variance for, you can pause this to make note of the different variance estimates. For the first university sample, we had 2, then we had 1.5, and then 2.5. So 2, 1.5, and 2.5 divided by 3, and we get, well, let's do the calculation. You know, why not? We'll see something in the chat, prove that I'm actually doing something. 2 plus 1.5 plus 2.5, close the bracket, divide by 3. A fairly simple calculation. The numbers work out nicely to just get a 2. I'll put a circle around it. A 2 for the within groups variance estimate. So that's half of the fraction. I like to do that one first. The other half is the variance between the groups that I'm trying to estimate as well. Put some squiggles under that. So I have 2 things to do in my calculation of my F statistic. Now this one is a little bit longer, unfortunately. Leave the best for last. So here, what am I doing? I am trying to see what the variation is between these groups. So I am going to treat each one as a single data point by using the sample mean, and then we'll compare those between them, sort of as a next level group of groups. Take a sample of these samples. So I'll have a super sample of 3 data points. The first one, I can't remember what they were. Let's go see. University X gave us a mean of 5. University Y gave us a mean of 4, and the last one a mean of 6. So 5, 4, 6. So a mean of 5, a mean of 4, and a mean of 6. Okay, so those are going to be my 3 data points, and I'm going to calculate the variance, or estimate the variance between those. As the name suggests, between the groups. So the mean of these means we'll call the grand mean. So it was a 5, and then a 4, and then a 6, and there were 3 of them, and so I just averaged them out, and conveniently I should get a 5. Just the numbers work very nicely today. So the mean of these means the grand mean. Now I have to estimate the variance of these. And variance is, of course, calculated. Let's go and see if there's a formula to help remind me way back. Ooh, not that far back. I went down, actually. Where am I now? Over here, 7.1, the variance estimate, where I take the sum of the squares, which means the squared deviations from the mean for each score, and I divide by n minus 1, the number of scores minus 1. So I will have to calculate for each one the score, difference from the mean, squared, divided by number of scores minus 1. Plus the next score, square deviation, n minus 1, or the number of scores minus 1. And the last one, square deviation divided by number of scores minus 1. Now this is a fairly simple calculation because this first one is just a 0, this one is just a 1 over 2, and this one is also a 1 over 2. So 2 halves give me a nice simple 1. However, there is a little catch that I can very easily miss or glance over. That this is a variance estimate for a distribution of means. These numbers are not individual population scores. They are sample means from samples of size 25. So this is a variance estimate of a distribution of means from samples of size 25. So let's just see if that helps, if there is a reminder for that in my formula sheet. So I have this over here, 9.2, which was just a new look to the familiar variance estimate calculation, reminding me that it is a variance of a distribution of means. I have to compare apples to apples, so to speak. In my F statistic, I'm comparing variance estimates of the population of individuals. So the within one referred to individuals, the between one has to refer to the same thing, has to be an estimate of the same thing so I can compare them. And right now it's unfortunately not. However, I can simply reverse a formula we've seen before. I'm looking for it. Formula 7.5. That in that case, where I wanted to find the variance estimate for the distribution of means from the individual one, I divide by n. Now I'm looking for the individual one given the left side, so I have to multiply by n. Now that is also written in formula 9.4, and there's a description there as well. The between groups population variance estimate is the estimated variance of the distribution of means that I have to multiply by the number of scores, the super sample size. So to get the variance estimate between, I'm going to take the variance estimate I found up here times 3. I'm pausing to see how you feel about the 3. It is not, it's a very easy mistake to make. It is the sample size that these means are referring to, not the number of groups that I've been working with in my super sample. So that's not right. Be careful. I did that on purpose to just check. It's so easy to do. I've seen a lot of people do this. It is the group size, because these means, the 5, the 4, the 6, refer to sample size, refers to means of samples of size 25. So that is the sample size. Okay, which is also why they're all the same. So these calculations are easier. All right. So then we get 1 times 25, which is 25. Did we put a circle or anything around it? Yes. Okay, so now, whoopsie, pen. Now we have separately found a variance estimate for within the groups. We have found a variance estimate between the groups. Now this seems, oh, this one's way bigger than this one. Yes, but how much bigger is okay? That is why we have a distribution. We just want to put these together for our F observed. Which one goes at the top? Which one goes at the bottom? Remember, between is at the top. So it's 25 over 2, which is 12.5. So that is our observed statistic. Now, I can't look at that and say, oh, that's big. Yeah, sure. How does it compare to my, just trying to manage my space here. So if I look here at the F distribution, it depends on the degrees of freedom, but let's look at that. My observed score, let's say, sits over here. Observed 12.5. I need to compare that to a cutoff. I'm just going to backtrack a little bit here. Before we put that in, redo. I can't redo. Oh, like that. Let's find, like we usually have, the cutoff so that I have an alpha there. That'll be our F cutoff. And we look at the table for F distribution, not the formulas, data table. Here's our F distribution. We have to keep in mind our numerator degrees of freedom, our denominator degrees of freedom. If you look back, degrees of freedom for the numerator, that was a 2, and the bottom was a 72. Now again, these tables are abbreviated, so we might not find the 72 exactly, and we unfortunately don't. This is our 2. We go down to the closest one, which is 70, and 4.92 is our cutoff F score, 4.92. We then compare that and see, ooh, our observed one is further out. F observed 12.5, past the cutoff, and therefore the evidence is considered strong enough to suggest that indeed there is a difference between these two, meaning that there's extra variance between the groups that's not among the groups as well. That has to come from the fact that these groups are actually different in terms of where they're positioned by way of their mean. So let's write that down and we will be done. So conclusion, since F observed is greater than our F cutoff value. We reject the null hypothesis in favor of the research hypothesis, of course, and say the evidence is strong enough. That's how we determine when is the evidence strong enough, when is one number bigger than another enough to go past just normal natural fluctuations. The evidence is strong enough to suggest that there is a difference in some sociability score, right? They didn't actually say just how sociable they are. Just measured some sociability. In sociability, whatever that means, among, or let's say between, that's maybe a better word, between the three universities. So just understand what we are doing here and what we're not doing here. We are simply trying to establish if there is a difference somewhere. Having found a difference, or the evidence suggests that there is a difference, we don't know where that is. We don't know where that is. We're fairly confident that we're not making the wrong conclusion, or we're making the wrong conclusion with a very small probability. There's always a chance. But even though we can confidently say there is a difference somewhere, we don't know. Is it between universities X and Y? Is it between all three? We don't know. So it is powerful in what it can do, but it doesn't do everything in one go. You have to have follow-up tests to then say, okay, we suspect that there is a difference somewhere between these groups. Let's go look at them sort of pairwise and find the difference, see which two are actually different. Or you could do that beforehand, suspecting that, for example, University X and Y are the ones that are different. So different approaches here. This is this ANOVA test is sort of doing a larger, just establish if there is a difference investigation. To actually know where the difference is, there is certainly more to do. However, this gives us hopefully a good idea of the basic flow through the hypothesis testing procedure for ANOVA and the calculations behind it. As always, let me know if you have any questions, and we will talk again in the next video. Until then.